Inside a standard home liquefied petroleum gas cylinder, a specialized balance of physics and chemical engineering ensures a safe and steady fuel supply for everyday domestic cooking. The vessel is specifically designed to store hydrocarbons, primarily propane and butane or a dynamic combination of both, under moderate pressure. Under this elevated pressure, the gas compresses into a liquid state, which significantly reduces its volume and allows a massive amount of potential thermal energy to be stored inside a relatively compact steel container. The dense liquid fuel naturally settles at the bottom of the cylinder, occupying the majority of the lower space, while a pressurized vapor space naturally fills the void directly above it. Unlike industrial cylinders, specialized liquid withdrawal systems, or autogas tanks that feature an internal dip tube to extract liquid fuel directly from the bottom, standard household cooking cylinders rely entirely on vapor withdrawal. The intentional absence of a dip tube ensures that liquid fuel cannot directly escape into household appliances, which would pose severe fire hazards and appliance damage. Instead, as fuel is consumed at the burner, the pressure inside the upper head space drops slightly. This sudden decrease in pressure causes a portion of the liquid at the bottom to boil instantly, a thermodynamic process known as auto-vaporization, replenishing the gaseous vapor at the top of the container. This continuous cycle maintains a steady pressure state inside the vessel as long as liquid fuel remains present. When the main control valve situated at the top of the cylinder is manually opened, the pressurized vapor naturally flows out of the head space without requiring any external mechanical pumps or complex machinery. The gas passes directly into the flexible high-pressure hose attached to the cylinder assembly. This reinforced hose acts as a durable, flexible conduit, engineered to withstand fluctuating internal forces, continuous movement, and environmental wear while carrying the pressurized gas safely toward the regulating assembly. The next critical phase in the fuel's journey takes place inside the precision pressure regulator. The gas inside an unregulated cylinder exists at a dangerously high pressure that fluctuates based on ambient room temperature. If this raw, high-pressure gas reached a domestic kitchen appliance directly, it would result in uncontrollable flames, compromised seals, structural failure, or explosive leaks. The pressure regulator houses a delicate internal diaphragm and calibrated spring mechanism designed to step down this high, variable cylinder pressure to a safe, extremely low, and remarkably consistent operating pressure suitable for standard home appliances. Once safely depressurized by the regulator, the gaseous fuel enters the home's fixed piping network, which is typically constructed from rigid copper tubing or specialized approved metal lines. Copper is widely preferred in residential gas plumbing due to its high corrosion resistance, structural flexibility, and capability to maintain tight, leak-proof mechanical joints over decades of continuous use. As the gas travels downstream through this copper pipeline, it passes through a secondary manual shut-off valve situated close to the appliance. This isolated valve provides an essential safety mechanism, allowing homeowners or service technicians to shut off the gas supply instantly during routine maintenance, long periods of non-use, or unforeseen emergency situations. After passing through the final shut-off valve, the low-pressure gas reaches its ultimate destination inside the kitchen stove assembly. Within the appliance, the gas flows through a tiny brass orifice into a venturi tube. As the gas streams rapidly through this narrow nozzle, it creates a localized drop in air pressure that pulls ambient oxygen directly into the stream, thoroughly mixing oxygen with the hydrocarbon fuel in exact proportions. This balanced fuel-air mixture then travels upward into the main burner head, where it exits through a pattern of small ports. Upon ignition, the optimal ratio of atmospheric oxygen and purified fuel produces a hot, clean, soot-free, and highly efficient blue flame, delivering safe and reliable heat for all daily culinary needs.